There is a specific moment in deep learning that every practitioner knows too well. You are training a large model, you have pushed the batch size as high as you dare, and suddenly the system crashes. The error message is unforgiving, out of memory. You are stuck because the graphics card has hit its physical limit. For years, the only solution was to buy a new card with more video memory, a component that has become increasingly expensive. But there is a way to bypass that limit without buying new hardware. It involves a technology often discussed in the community as Nvidia GreenBoost. This approach allows the system to transparently extend your graphics card memory using your computer's system RAM or even your non-volatile memory express storage drives. It creates a unified pool of memory that the operating system and the graphics driver can manage automatically. The promise is compelling. You can run larger models on consumer hardware that would otherwise fail. But promises are only half the story. The real question is, how much speed do you lose to get that extra capacity? To understand the performance impact, we need to look at how this memory extension actually works. When the graphics card fills up, the kernel-level solution begins to page out data. This is similar to how your computer uses a page file on your hard drive when your RAM runs low, but it happens specifically for the graphics processing units. The system takes chunks of data that are not currently being used by the active threads and moves them to the slower storage medium. When the graphics card needs that data again, it fetches it back. This process is transparent to the application, meaning you do not need to change your code. However, the speed difference between the native video memory and system storage is massive. Video memory is designed for extreme bandwidth and low latency. System RAM is slower, and non-volatile memory express storage is significantly slower still. Imagine you are a librarian managing a library. Your desk represents the video memory. You can only hold a few books on your desk at any given time. The rest of the books are in the stacks, which represent your system RAM or storage. When a patron asks for a book, you want to hand it to them immediately. If the book is on your desk, it takes a second. If the book is in the stacks, you have to walk down there, retrieve it, and bring it back. That walk represents the latency penalty. Now imagine you are running a real-time inference task. This is like a librarian who must answer questions instantly. Every time a patron asks for a book that is in the stacks, there is a delay. In a real-time scenario, that delay accumulates. You might be able to process a request, but the response time will suffer. If the system has to swap data constantly, the latency spikes and the user experience degrades. Now consider batch training. This is a different scenario entirely. In batch training, you are processing a large dataset over many hours or days. You are not waiting for an instant response from a user. You are feeding the system a massive pile of data and letting it crunch through it. Here, the throughput matters more than the latency. You can afford to have the librarian walk back and forth to the stacks because the goal is to get the whole job done eventually. The system can optimize the order in which it retrieves data to minimize the walking time. This is why memory extension tools often work better for training than for inference. The system can schedule the memory swaps during periods of lower activity. It can prefetch data before it is needed. In a training loop, the GPU can remain busy most of the time, even if it has to wait occasionally for data to arrive from the system RAM. However, even for training, there are hard limits imposed by the physical connections. The data has to travel over the peripheral component interconnect, express bus. This is the highway connecting the graphics card to the rest of the computer. While peripheral component interconnect express has improved over generations, it still has a finite bandwidth. When you are moving large tensors of data between the graphics card and the storage, you are saturating that highway. If the non-volatile memory express drive is fast, it still cannot match the internal bandwidth of the graphics card. The bottleneck shifts from the storage drive to the connection itself. You might see the drive write at 10 gigabytes per second, but the peripheral component interconnect express lane might only handle half of that effectively when shared with other tasks. This creates a ceiling on how much performance degradation you can expect. There is a nuance in how this technology is implemented. Some solutions rely on the operating system to manage this paging, which introduces overhead from the central processing unit. The CPU has to decide what to move and when. This adds latency because the graphics card has to wait for the CPU to give it permission to access the data. Newer architectures are moving away from this model. Research into GPU-driven unified virtual memory suggests that offloading the page migration logic to the graphics threads themselves is more efficient. This reduces the CPU involvement and allows the graphics card to manage its own memory hierarchy more intelligently. We see this in advanced architectures like the Grace Hopper superchip, which uses hardware-level cache coherent interconnects. This allows direct access to system memory without the traditional operating system overhead. But for consumer hardware, we are still largely relying on the software-defined virtualization approach. This brings us to the cost-benefit analysis. Is it worth the trade-off? For many researchers and hobbyists, the answer is yes. The cost of a new graphics card with double the video memory is significant. Extending the usable lifespan of an existing card by leveraging cheaper system RAM and non-volatile memory express drives changes the economics. You are trading speed for capacity. If you are training a model that will take days to complete, saving thousands of dollars on hardware is a valid trade for a 20% reduction in speed. But if you are deploying a model that needs to respond to users in milliseconds, the latency penalties become unacceptable. The system might run, but it will not be real-time. The open sourcing of these kernel modules indicates a community-driven shift towards solving memory bottlenecks. It suggests that future hardware architectures may increasingly rely on software-defined memory pooling rather than just raw video memory capacity. We are moving towards a world where the distinction between system memory and graphics memory becomes less rigid. But until the hardware catches up to the software, we must respect the physical limitations of the peripheral component interconnect express bus. The technology allows us to run larger models, but it does not make them run faster. It simply allows them to run at all when they otherwise would crash. Understanding the difference between latency and throughput is the key to knowing when to use it. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.